Thank you. So, hi everyone. Today my talk is can data assimilation of physics and biological satellite observations inform the subsurface distribution in the Gulf of Mexico? When we talk about the data assimilation, the first question might be why we need data assimilation and what is the data assimilation? As we know, the numerical models are powerful tools, but they are imperfect representation of the nature systems, and so they suffer from different uncertainties. These uncertainties may come from like the model resolution, model input, the biological parameters, such as for the biological model and its structure. So the data assimilation is the statistic tool to help us construct the model performance by combining the information from both the numerical model and the observations. And here we will use one example to illustrate the data assimilation. This figure shows the front of the current and the current eddies in the Gulf of Mexico observed by the satellite observations and from the model results with or without the data assimilation. So we can see that when without the data assimilation, the free model run, which is represented by the blue lines, is quite different from the black lines from the observations. And with the help of the data assimilation, the model results become much more similar with the observations. So this is one aspect of why we need the data assimilation and what the data assimilation can do. In the biological oceanography, the data assimilation is less major than in the physical oceanography because of the insufficient biological observations. Currently, the satellite estimates of surface chlorophyll is the major source of observations to be assimilated into the biological model. But we know that the satellite observation is limited to the ocean surface and hardly provides the information below the surface, which is not homogeneous but may be very important for the whole ecosystems. So here we use one example in the Gulf of Mexico. So this is the surface chlorophyll concentrations from the satellite observation, and this is the subsurface chlorophyll distribution from the BGC algal float. And we can see that they are not homogeneous in the vertical directions. In recent years, the fast growing of the BGC algal flows make it possible for us to measure the multiple biological properties at the same time in relatively high spatial and temporal resolutions, and they naturally supplement the satellite estimates. But currently, the BGC algal flows are still very sparse for 3D data assimilation, and their applications are still limited. This not only limits the data to be assimilated, but also limits the scale assessment of the biological data assimilation. Only a few studies compare their model results with the observations below the surface, and it makes us poorly know about the data assimilation's performance below the surface. In addition, the biological traces can be transported and diffused by the 3D circulations, and so only assimilating the satellite surface chlorophyll is not sufficient when the biological model is capable to bias the physical model. So the assimilating the physical observations into the coupled physical and biological model has been explored, hoping that the improved physical circulations can result in a better simulation of the biological model. So that's the motivation of this study. And in this study, we will explore whether assimilating the current major observation streams, including the satellite observations of physical and biological properties, can constrain the model performance, especially the biological aspect below the surface. We choose the Gulf of Mexico as the study region because in the Gulf of Mexico, the loop current and its associated mesoscale eddies are stochastic and have to be assimilated accurately without the data assimilation. In addition, these mesoscale features can also influence the biological properties below the surface, such as the position of the nitric oxides, the deep chlorophyll maxima. We also hope that by assimilating these physical observations in addition to the satellite surface chlorophyll can help us construct these biological mesoscale features in the Gulf of Mexico. So we have 3 different experiments. The free run is the deterministic model run without any data assimilation. the DSS run assimilates the satellite data, including SSH, SST, and sea surface chlorophyll. And in the DARGO run, we also assimilate the ARGO profiles of temperature and salinity to test their values for the biological data assimilation in a calculated and biological model. And then we will compare our model results with 5 BGC ARGO float in the Gulf of Mexico, which is used as the independent validation in our study. And so this enables us to evaluate the biological data assimilation's performance below the surface in a fine resolution scales. So let's look at the model results. This figure shows the monthly average front of loop current and loop current eddies from the satellite observation, the free run and 2 data assimilative runs. Actually, I have already shown one of this panel before. So without the data assimilation, the free run blue lines can be quite different from the black lines from the observations. And with the help of the data assimilation, these 2 data assimilative runs, which is represented by the orange and yellow lines, can reproduce the very similar features with the of the loop current and loop current eddies with the observations. This indicates that in our case, the data assimilation is able to correct the major circulation features in the Gulf of Mexico. And as a result, the SSH and SST were naturally improved. So here we show the comparisons of root mean square errors for SSH and SST between the free run and the 2 data assimilative runs. The red color represents high level of root mean square errors in the free run, and therefore represents the improvement by the data assimilation. So we can see that for the SSH and SST, they were both improved almost everywhere in our model domain. And for the SSH, the largest improvement was obtained in these regions, which is influenced by the loop current and loop current eddies. We also showed overall relative improvement by these large numbers. So in general, the data assimilation improved the SSH by more than 50% and improved SST by more than 30%, quite close to 40%. Well, this is the similar figure, but for the surface chlorophyll. So in assimilating the satellite data can also improve the satellite surface, can also improve the surface chlorophyll almost everywhere in our model domain. But in the DARGO run, when assimilating the ARGO profiles of temperature and salinity, it will yield lower reductions in the root mean square error and even more deteriorations in the surface chlorophyll, which can be seen from the blue regions in this figure, and can be also seen from their histogram of relative improvement by the data assimilation. So in this figure, the positive values represent the improvement by the data assimilation, and the negative values represent the deteriorations by the data assimilation. So the improvement by the data assimilation was not limited to the surface layer, but also extend to the subsurface and even deep waters. Here, this study showed the vertical profiles of root mean square errors for temperature and salinity with respect to the independent BGC ARGO profiles. The blue lines represents the free run, so we can see the natural reductions in the root mean square errors for temperature and salinity below the surface. And this improvement can extend to more than 1,000 meters for the temperature and above 800 meters for the salinity. The numbers shown here also represent the overall relative improvement by the data assimilation in terms of the root mean square errors for temperature and salinity. We also show the subsurface distribution of the temperature following each BGC ARGO float to illustrate how the data assimilation corrected or improved the subsurface temperature distribution. So in general, the 2 assimilative runs have the better agreement with the observations than the free run. And the numbers here show the overall relative improvement by the data assimilation following each float. So we can see that the largest improvement by the data assimilation is obtained within this float, within the float 287, where the relative improvement is as high as 60%. We also use this animation to show the trajectories of these 5 BGC algal float, and also the temporal evolution of SSH from the satellite observations. So we can notice that the float 287 here, which is represented by the green lines, pass through a new and very energetic loop current eddy. So let's zoom into the subsurface distributions within this float, within the float 287. Okay, so the top panel shows the measured and modeled SSH. The middle panel shows the temperature distribution, and the bottom panel shows the temperature bias in relative to the observations. The warm color represents the model overestimation, and the cool color represents the model underestimation. So we can see that the data assimilation corrected the position of this loop current eddy, and also within this loop current eddy, the data assimilation depressed the isothermal noise, and therefore naturally decreased the temperature bias in relative to the observations. In addition, the improvement in the temperature will then translate into the subsurface nitrate because of the high correlations between the temperature and nitrate. So we also show the nitrate distributions following this float, and we can see within this loop current eddy, the data assimilation also depressed the nitrate counts. Although our BGC algal float didn't measure the nitrate distributions, we can estimate the nitrate based on their climatological relationship with the temperature. So this climatological relationship is derived from the data collected in the Gulf of Mexico by the World Ocean Atlas. And we compared our model results with this regressed nitrate and find that the unbiased root mean square errors for the nitrate within this float was reduced by about 40%. If we take all of these 5 BGC algal float into account, then overall relative improvement is about 30%. So next we will look at the subsurface chlorophyll. Where the data assimilation impact on the subsurface chlorophyll is more complicated than the temperature and nitrate. First, we can see that either with or without the data assimilation, our numeric models can well reproduce the mean vertical profiles of the chlorophyll, but the models fail to reproduce the natural spatial and temporal variabilities of the chlorophyll profiles. So here we use the float observation and the free run to illustrate this. The top panel shows the SSH, and the bottom panel shows the subsurface chlorophyll distributions. The red line on top of this figure indicate where the deep chlorophyll maximum is. So based on the observations, we can see that the subsurface chlorophyll distribution, especially the position of the deep chlorophyll maximum, is highly correlated with the SSH. So for example, when the SSH is very high, like here and here, this indicates that the BGC algal float might be in an anticyclonic eddies, and in this case, the deep chlorophyll maximum is depressed and relatively deep. But in contrast, when the SSH is low, like here and here, this means the BGC algal float might be in a cyclonic eddies, and in this case, the deep chlorophyll maximum is elevated and shallower. But when we look at the free run model results, we can see that the modeled subsurface chlorophyll distributions are much less sensitive to the SSH than the observations, and the subsurface distribution of chlorophyll and the position of the deep chlorophyll maximum are more stable than the observations. That's why the data assimilation really improves the subsurface chlorophyll in our case. Even in the float 287, where the most predominant improvement of temperature and nitrate were obtained. So we guess this is because we use the suboptimal choice of night parameterization, because at these steps, the synthesis of chlorophyll and the growth of phytoplankton is more limited by the night rather than the nutrients. So we did some sensitivity tests by using one alternative night parameterization, which has more emphasis on the self-shielding effect of chlorophyll. So that means the subsurface night intensity will be more sensitive to to the chlorophyll concentrations in the upward corners. Okay, so here we show the subsurface chlorophyll distributions following the float 287, and we can see that when we use the original data, when we use original night parameterization, the data assimilation really depressed the deep chlorophyll maxima within this loop current eddy. This makes sense, but the subsurface chlorophyll concentrations is much lower than the observations. And when we use the alternative night parameterization, the deep chlorophyll maxima is even deeper and closer to the observations. And more importantly, the subsurface chlorophyll concentrations at these steps is naturally increased in this case and closer to the observations, even though the model underestimation remained. So we also plot the mean vertical profiles of the nitrate, the night intensity, and the chlorophyll concentrations within the center of these loop current eddies to see why. So the blue lines represents the free run, the orange lines represent the data assimilative runs. The dashed line represent we use the original night parameterization, and the solid lines represent we use the alternative parameterization. So we can say that by using alternative parameterization, the data assimilation depressed the deep chlorophyll maxima. And in this case, the magnitude of the deep chlorophyll maxima is much larger than the model case when we use the original night parameterization. Even although the nutrients distribution are very similar, are almost exactly the same. And this is because the alternative night parameterization reproduce the elevated night intensities at these steps because of the reduced chlorophyll concentrations in the upward corners. But the original parameterization didn't resolve these features. So finally, here's our major conclusions. Assimilating the satellite data can improve the major circulations in the Gulf of Mexico, and then this improvement will extend to the subsurface for the temperature and salinity, and then translate into the subsurface nitrate. But the subsurface chlorophyll is more complicated and better improved by the data assimilation. When we improve them, because we use the suboptimal choice of the night parameterization, and if we improve this night parameterization, then the subsurface chlorophyll can be further improved. So that's it. Thank you.
Great, thanks. Very interesting talk. I believe we had some questions already in the middle of the talk. Let me get the chat out. Yeah, we had a question from Yo-Yu in the DA sat run. Do you not assimilate Argo temperature and salinity, only sea surface height and sea surface temperature, etc.?
Okay, so in the DA sat run, we didn't assimilate the Argo profiles. We only assimilate the satellite data. Okay.
Thanks for that clarification. Are there any other questions out there? Does anyone have a question for Ben? Well, looks like maybe I've stunned everyone into silence. So, going once, going twice, we'll just leave it at that. Thanks a lot, both to Min and Lena, for really excellent talks. And we'll see everyone next week. Okay.